Good evening all, and welcome back to the WTF. And today we are doing something a bit different actually, playing around with a bit of medical electronics. And I'm just sort of seeing if I'm still alive. Yeah, still alive. So what you're listening to is actually a doppler machine, which is a tool that we use quite often in the hospitals, and as a vascular surgeon, which is my day job, we use machines, well, very similar to this, but actually quite a bit smaller, and they're quite useful pieces of kit for assessing blood flow, particularly in the legs, which is often the area that we often find ourselves where people need various things doing to improve the circulation. And I would say a Doppler machine is very much like the equivalent of a multimeter that you would use in electronics. So it's quite a nice piece of diagnostic equipment. And whenever you think of medical electronics, you always think, oh, they're ever so complicated, it's really expensive. Well, I actually decided to see how hard it can be and build my own Doppler machine, which we'll have a quick look at. So what is it? Well, without getting too involved in the Doppler effect, I mean, the Doppler effect is something that you often hear, but sometimes you don't always necessarily know much about it. I mean, if you look at any physics book, you'll get a good idea of what the Doppler effect is all about, but the easiest way of describing it is the sort of apparent increase in frequency that you get on the part of the observer when you have something that's making a sound or emitting a frequency that's moving towards you or away from you. So the easiest example is an ambulance. So when you hear an ambulance or a fire engine going past you, you tend to sort of have that funny increase in the pitch of the siren, and as it goes past, it sort of goes back down again. So you go beep-bor, 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 sort of like that. So that is the Doppler effect, okay? And this machine basically uses some piezoelectric crystals in the probe to emit some ultrasonic waves, which are emitted, bounce back off the moving blood in the artery, or whatever vessel you're probing, and that signal is then received by the machine, or by another crystal I should say, in the probe, and then it's amplified, and then what you hear is what comes out of this this particular unit, or whatever unit you're using. Now the ones that we use in the hospitals are not quite as big as this. They're sort of more sort of pocket size, quite modern versions, quite modern pieces of equipment. They'll sit in your coat pocket. Majority of them in the UK, most vascular units, they use them. They're made by a company called Huntley, which, from what I understand, is actually based not too far from here in Cardiff. So they as for nice little machines, they do the job. But I would say they're probably a bit flimsy. They're made plastic things about the size of a calculator or a bit bigger. And they do get knocked about a bit, and they do tend to break. So this thing's obviously the one I made, which is a bit more sturdier, and hopefully won't be quite so prone to breaking. Anyhow, what we're going to do is we'll have a closer look at this machine, and then we'll have a quick look what does it look like inside. I'll show you the circuit diagram, just to show how actually quite simple these machines are to build. And yeah, I hope you enjoy it. It's something a bit different from engines and amateur radio, but if you can, nice piece of equipment to use in the day job. Anyway, let's crack on, and we'll have a quick look at it. So as you can see, this is the Doppler machine that I've made. It's not an awful lot to see in terms of the controls. There's not much to it really. You've got on off, that's a VU meter, which isn't terribly sensitive. There's a rechargeable battery, and then that gives you your battery volts. You've got a volume, and then we've got the two plugs here for the probe. I'll show you the probe in a minute because it's actually quite interesting. It's you can see what, how it's been made. So what I did is I built all this up into a spare box that I had, a test set, which actually came from some old aircraft equipment, and the Doppler machine actually fits quite nicely in there. And I've got another little compartment there which I've got some foam to keep the probe in, and also there's a charger as well, which charges the rechargeable 12-volt battery. So just to show you how we use one of these, just for sort of general detection of blood flow. So I'll turn the volume up. I've put some ultrasound jelly there. So we can just trace the radial artery all the way around here actually. And one of the things you look for when you examine or when you get experience of doing this, you can listen to the quality of the waveform. I mean, some of these machines have recorders and visual representations of the actual waveform. Just turn it off for a minute. The actual phasicity, what they call the phasicity of the waveform, is quite important. It gives you an idea of the nature of the blood flow. So, for instance, if there's a obstruction in one of the blood vessels higher up, you get a change in the waveform, which will give you an idea, as to the how, if the blood flow is being restricted. So normally, in a normal healthy individual, you have typically what they call a triphasic waveform, Doppler waveform, and the reason for that is that you get initial sort of peak in your blood flow, and then you get a rebound due to elasticity of the vessel wall, and so you get a classic sort of triphasic waveform. It's a bit difficult to demonstrate with this machine. I think some of them are more modern ones which have a bit more sort of better audio processing and filtering, sort of demonstrate it quite well. So that's one of the things you look for. And the other thing that you use these machines for, which is the sort of more common use, is for measuring the pressure in the circulation or in the blood vessels of the legs. And what you would normally do is put a blood pressure cuff around the ankle, and then using this Doppler machine you would detect the Doppler signals over, say, the ankle pulses, and then by using the blood pressure cuff, pumping it up, and then seeing when the signals disappear and reappear, you can then determine the perfusion pressure in the foot. And we call that the ankle brachial pressures, or ankle brachial pressure index, when you compare it to the blood pressure in the arm. So that's quite a common way of assessing circulation in vascular patients. Anyhow, let's take a look at this probe a minute. This probe's quite interesting. Hopefully we'll try and get some up-close shots of this, because then you can see exactly how it's made, and figure out the sort of transmitter and receiving crystals that are in this probe, which you can actually see because of the way this one's made. Okay, so we've got the probe just lightly clamped in the vise, just to keep it steady. And there's not much to these actually. It's just a piece of aluminium tubing, and at the end of it you've got two crystals. Now those square things that you can see, there's two of them. Those are actually the piezoelectric crystals. Now they're not well, I think probably in the older machines might have used quartz, but I think these ones are made of a special piezoelectric ceramic, which I believe is called PZT, which is a sort of mixture of various oxides of various metals, which has better piezoelectric properties than quartz, which is, you know, those radio amateurs among you will know that quartz, it makes a very good piezoelectric oscillator, and you know, we've used crystals for all sorts of things in amateur radio, transmitters, receivers, filters, etc. So this is these are ceramic, and they emit signals in the order of, well, this particular probe is an 8.2 megahertz probe, and so those are ultrasonic waves. When that piezoelectric crystal vibrates, it's emitting ultrasonic waves at about 8 megahertz. You do get different frequencies. Just to give you an example, so 8.2 megahertz or 8 megahertz is sort of commonly used for in vascular surgery for sort of insunating blood vessels, which are relatively close to the surface. So if, for instance, you were wanting to make up an ultrasound machine or a Doppler machine, say for listening to a baby's heartbeat, you know, in pregnant ladies, then you wouldn't use this type of probe. The signal would get attenuated too quickly. So you go for something like a probe which is in the order of 2 megahertz. So the fetal Doppler machines are usually sort of around about 2 megs. And these ones, and the vascular probes do go up. I've got a machine here which does actually go up to about 9.4, 9.6 megs. So, you know, generally the higher the frequency, the more superficial the probe tends to be used for. And other than that, there's not much to it. It basically has 2 coax cables with a couple of phono connectors on it, which plug into the Doppler machine, and that's it. If we have a look at the circuit diagram, you can see that actually this Doppler machine is relatively simple. In fact, a lot of the principles here and this circuit diagram are really taken from technology which we often use in amateur radio, funnily enough. So if we look at the top here, this is actually the receiver section, the oscillator section of the Doppler, and we've got sort of like a source follower type oscillator. I think that's correct. I'm not so clued up on FET oscillators as other ones, as valve oscillators, but anyway, so we got a little oscillator here and a 2N3904 which acts as an amplifier, and we got this effectively is a tuned circuit, and also here's a tuned circuit, and then this connects to your Doppler probe. For those who want to build this, these tuned circuits are roughly about 5 or 6 microhenries, and also with these ones with slugs in them, so you can, you know, just sort of standard radio coils will do about 6 millimeter in diameter, and seems to be quite stable. I didn't have any problems getting this thing to oscillate. It sort of worked more or less first time. So the bottom here, we've got the receiver section, and I did actually change a couple of things on this circuit diagram to sort of more commonly available transistors. This PN2369A, you can substitute that for a BC 547 or something like that, or any sort of bog standard NPN transistor. This base actually connects up there. I actually forgot to put that in the circuit diagram. That base, that transistor connects there. And again, you've got a tuned circuit here, which basically picks up the Doppler shifted frequencies. You've got which goes to the gate of the 2N5485, and then you've got a tuned circuit here. That's about 22 PF, as far as I can remember. And again, similarly, I think the inductance was about 5 microhenries, not far off from there. I think the demodulated signal then sort of comes through here. You've got a diode, that's a 1N4148, again, sorry for not putting that in, just a bog standard signal diode. And then your signal, the demodulated audio, is then amplified through this FET. I think this, I think what this transistor does here is sort of delays the switching on. Not quite sure the purpose of that. You would probably work without that, but if anybody thinks otherwise, just let us know in the comments. And then we go to an audio amplifier, which hopefully I can show on this next picture. So you've got some more amplification there with that FET, and then you've got an old favourite here. For those people who do amateur radio and are familiar with QRP rigs, you'll notice the LM386, the ubiquitous 3-watt audio amplifier chip. Now this you have to be quite careful with, because it does tend to sort of self-oscillate if you're not careful. The gain is adjusted with this capacitor and this resistor, which you can play around with. But what I would say is that make sure you put a quite sizable capacitor. I think they've got it shown here. But this capacitor and this 0.1 microfarad decoupling capacitor really has to be right close to this power leg as possible to avoid this thing going into self-oscillation, because the whole crux of this Doppler receiver is it really relies on amplification of the audio more than anything else. So therefore this part of the circuitry is quite crucial. You know, when you do it, you have to mount it on a ground plane, keep everything, all the leads as short as possible to avoid it from self-oscillating. So that's more or less the circuit. One of the things that I noticed about building this Doppler machine is that it's quite important to make sure you've got a half decent ground plane. On my initial version, my prototype, call it what you like, which was made on some sort of standard Vera strip board, and what I noticed was that the LM386, which is down there, was quite sensitive and would quite frequently sort of go into self-oscillation and become unstable. So this actually is the Mark II version of the board, which I've sort of built kind of like point to point, if you can call it like, bits of strip board and glued on to mount the various components. And what I found that using a copper clad board certainly makes a big difference. So if you're thinking of building something like this, just bear that in mind, and use something like a copper clad board, or if you want to go the extra mile, you can always do a proper PCB. I haven't got much patience with doing my own PCB, so I thought I would just do it like this. Anyhow, I'm just going to grab a pencil and quickly show you what's what. So in terms of the layout, I don't think it's too critical, but it just makes sense to keep. This is the transmitter section, and then you've got the receiver section sort of along here, and then the audio part is at the back. It seems to work for me. I don't think it would be wise to sort of mix up the receiver and the transmitter sections, because you're probably going to get interference. And the other thing as well is, talking of interference, it's quite important to have these different coils screened, and I used some old radio coils which I sort of unwound and rewound to do that. Moving on, this little board here is merely the board for the VU meter, which is quite a useful touch. Not essential by any means, but I thought it would sort of be a quite nice touch. And that's about it really. So I'm going to mount these inside the box and do a bit of painting, do up the panel, so hopefully we should have the finished article. Anyway, folks, that's my little Doppler machine, which seems to work pretty good actually. We'll might take it along to outpatients and ask somebody, one of the patients, to volunteer to see if we can try it out. Yeah, quite pleased with that. Anyhow, till next time, hopefully we should have some more jet engine stuff for you soon. Keep watching and see you again soon.